Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. We are in the chapter 11 now, and in the last two classes we have discussed about the leaching and extraction process. Leaching and extraction is a separation technique similar to that adsorption or distillation or crystallization. However, the difference is that this has certain advantage over the distillation or crystallization, evaporation, those kind of method, because here we do not need excessive high temperature. We can separate the solute, a particular solute component which is in a component mixture by some other phase, maybe by some other liquid phase, and we can separate the particular component without application of heat. Okay. So, for heat sensitive material, leaching and extraction is very important, and it is also important when we have very dilute solution of a particular component that we want to separate. And in food there are many application of leaching and extraction we can find. Some of them we have discussed. Leaching is basically when the solid component comes into contact with a solvent, and a particular solute from the solid is being separated because that solute has a particular affinity towards a solvent. Okay. But when instead of solid we use two liquid phase, okay, two liquid phase, and one component from one liquid will be extracted by the other liquid, then we call it extraction or solvent extraction. Okay. So, both the method, either solid liquid extraction or liquid liquid extraction, these two are very important in food processing. We have seen that green tea extraction, if you want to develop green tea from the green tea leaf powder or granules, or if the caffeine, if the coffee beans are used for extraction of the caffeine. So, all these are application of leaching, and extraction is used when some let us say some component of the oil or flavor that we want to separate by utilizing some other solvent, and then we call it extraction. Okay. So, basically for oil we definitely use that solvent extraction technique, and all these two cases we need to know few conditions, okay, and few parameters. So, some of them we have discussed in our previous two classes. One is the equilibrium condition, because these two separation techniques are actually the molecular transfer techniques. Okay. The solute molecule is moving from one phase to the other because of the difference in the chemical potential or difference in the concentration. So, this molecular transfer will occur unless there an equilibrium will be established, right. So, when the equilibrium will be established, then this process, the transfer of the solute from one phase to the other will stop. So, that equilibrium we have discussed the equilibrium for single stage leaching operation in our last class. Today we will solve one problem on that, and also we have seen the multi-stage leaching, where the single stage operation is repeated the same way we can perform for the multi-stage, and we can assume that the transfer, the rate of transfer will be same, the rate of transfer of the mass will be same in each phase, and eventually the equilibrium will be attained. So, basically by equilibrium we want to mean that the chemical potential of the solid phase from where we are extracting the solute, or the slurry that we call it, and the extract, the solvent that we are using. So, in this two stream, when the chemical potential of a particular solute will be similar, then the equilibrium will be achieved. Now, this is an ideal case. It may not happen that ideally if for a finite period of time the contact between the slurry and the solvent is taking place. So, may not be the ideal situation we can find. So, for that we have to make this contact for a longer time, okay, for an infinitely long time, so that this equilibrium will be reached. So, in ideal case we may get some deviation. So, the concentration or the fraction of the solute in the slurry and solvent and in the extract may be different. Okay. So, we have seen that we have also seen the how to draw the curve between the inert fraction in the solute plus solvent stream and with the solute fraction in the solute and solvent stream, how the equilibrium diagram can be drawn for the leaching, and also we have seen that how the operating line and the equilibrium line can be plotted for a single stage operation. Now, we will solve a problem, and this problem is based on the multi-stage. In the previous class we have discussed the phenomena that happen in a multi-stage, although it is similar to the single stage only, and it is a counter current flow. So, in a counter current leaching, from the one side the crushed bean, this is our the solid mixture that is entered, okay, and from the crushed bean we want to extract the soya oil that we want to extract, and there is a solvent that is entering into the multi-stage leaching apparatus from the opposite side. Okay. So, this is a counter current operation. Now, let us see what is the question, and then step by step we will try to solve it. So, the question is, oil is to be extracted from soya bean in a counter current stage contact extraction apparatus. Okay. So, multi-stage, and there are different stages are there. In every stage the beans, the solid material and the solvent are coming in close contact, and initial content of the initial oil content of the bean is 18%. Okay. The final extract solution is to contain 40% of oil. Okay. So, the extract that we are getting at the end, that is the solvent plus oil. So, that should contain 40% of oil, and 90% of the total oil is to be extracted. That means, the bean has some amount of oil, that is 18%, and of that 90% oil should be extracted. Calculate the number of contact stages that are necessary to separate this 90% of the initial sample. Assume that the oil is extracted from the beans in the first mixture, that equilibrium is reached in each stage, and that the crushed bean solid in the underflow retain in addition half their weight of the solution after each settling stage. So, we have seen while in the single stage we have seen that if this is your extraction, okay, this is your extraction vessel, let us say, for a single stage, and when your solvent is coming into it and the solid is also entering. So, there will be overflow, which is having your solvent plus solute that we want to extract, or maybe solvent plus oil that you want to extract, and the slurry will be your underflow. Okay, slurry will be your underflow. So, here it says that okay, so crushed bean solid in the underflow retain in addition half their weight of solution after each settling stage. That means, after one stage, let us say the beans is having 18% oil. So, if we take total 100% material is coming into the system. So, in a first stage 18% is the oil. So, 82% will be the solid beans, solid material. So, in the underflow this 82 will go, along with that half the solution will be going. So, plus 41 this much kg of the material will have solvent plus some solute, okay, because not all the solute will be extracted, 90% will be extracted. So, this is how we can approach the problem, and let us see we have solved it for some stages, and before going into that just I will once again remind you the equation of material balance and component balance which is used in the multi-stage. So, in the multi-stage, as okay, this is the multi-stage diagram and this is the V n plus 1, that is the solvent entering into the nth stages, and L A, that is the solid material or from which we need to extract a particular component or solute or oil, that the rate is L A. Okay. This will be equal to V A plus L N, where V A is the V A is the solvent or the extract that we are getting from here, and L N is the slurry from the nth stage. Okay. Similarly, when we do the component balance in that, so V n plus 1 into X n plus 1, that is the concentration of the oil or solute, the particular component that we want to separate, that in the solvent itself, and similarly X A denote that the component fraction in the extract that is coming out from the first stage, and L A Y A. So, Y A is the fraction of that solute component in the feed stream, and Y N is the fraction of that solute component that coming from the nth stage. Okay. And from these two we can eliminate V n plus 1, okay, and then we develop this equation just taking V n plus 1 from here, and then we put in the balance equation. So, L n plus V A minus L A, that into X n plus 1, that is equal to V A X A plus L n Y n minus L A Y A, and from here we can get the X n plus 1 as this Y n into L n by L n minus L A plus V A plus V A X A minus L A Y A divided by L n minus L A plus V A. So, this is the material balance and overall mass balance or material balance and the component balance on the solute. So, this we will use now to solve the problem. Okay. So, we can see that V n plus 1 is the solvent entry in the nth stage, X n plus 1 the concentration, the fraction of that solute in the stream, L n Y n is the slurry that comes out from the nth stage, X 0 or X A we can take this as, because we have used this notation L A, Y A, X A and V A, right. So, heavier phase means the feed slurry that entered. So, that is we have assumed same, because this is the condition given that the rate of transfer will be same in each stage, right. So, L n plus 1 that is equal to L n, that equal to L A, that equal to L. So, this that the stream that is entering in each consecutive stages are same. Similarly, the lighter phase, so V n plus 1 that is equal to V n, that is equal to V A, eventually V. So, this stream is also having same heavier phase and lighter phase. Lighter phase means the solvent, heavier phase means the feed stream or the feed slurry. And we have got this applying this to in the previous equation, X n plus 1 equal to Y n L by V plus x a minus y a L by V. So, we had first the material balance equation and component balance equation, from where we got some expression of x n plus 1. Now, considering these two approach, we are simplifying the equation of x n plus 1. So, you can see now we have mentioned that, let us say 100 kg basis, if we start 100 kg raw material, that is raw soybean crush material we have taken, in that 18% oil was there. So, 82 kg bean solid was there, right, and 18 kg oil. Now, in the final underflow, so what will be going there? Some oil will be extracted, but most all the solid will be going in the underflow. So, in the underflow 82 kg bean solid will be there, and it was mentioned that half of that amount of this bean solid will be the solution part, because we have discussed this, that during leaching we can't get the dry solution initially, we will get two section, underflow and overflow. Overflow will have the solvent and the solute in it, and the underflow will have all the solid slurry material and some solvent, and that solvent will have some solute, and the concentration or chemical potential of the solute in that underflow stream and the overflow, if these two are equal, then only the equilibrium condition arise. Okay. So, that stream, the underflow stream, will have half of the weight of the micella will be the solution. So, 41 kg of solution. Now, the solution will contain 10% of the initial oil in the bean, because it was mentioned that in the question that 90% of the oil was extracted, right. So, 10% means 10% of this 18 kg, okay. So, 1.8 kg. So, that 18 minus 1.8, this has gone to the overflow, right. So, 18 minus 1.8, so 16.2 kg of oil in the final overflow, right. Now, it also mentioned that this much, that is that oil is coming into the solvent, but it will have 40% of the solvent, because solvent is having 40% concentration of the oil, okay, in the extract. So, the extract contain 60% solvent and 40% solute. So, if 40% is equal to this 16.2 kg, what will be the 60%? So, that is 16.2 into 60 by 40. So, we are getting 24.3 kg of solvent. Okay. Now, the total volume of final overflow. So, overflow will have the solvent plus the oil in it. So, 16.2 plus 24.3, so 40.5 kg, right. Now, the total solvent entering that we need to find. So, if you remember, we had 41 kg solution, and in that solution we had 1.8 kg of the oil material. So, what was the solvent? So, 41 minus 1.8, so we are getting 39.2. So, that 39.2 kg is the total solvent that has gone to the underflow, and 24.3 that has gone to the overflow. So, total solvent was 63.5 kg. Now, note that the solution passing as overflow between the stages is the same weight as the solvent entering the whole system. So, the solution passing as the overflow between the stages is the same that has entered into the system. So, that is 63.5. Now, this we have to see in all the stages what is happening. So, this is the overall balance. So, 100 kg in the underflow, we are getting beans 82, we are getting bean solid 82, oil 18, overflow solvent is 63.5, So, total is 163.5. Okay. Now, then from the 100 kg basis, 100 kg bean underflow, that will be extracted bean plus solution. Okay. So, that is 82 plus 1.8 plus solvent, that is 39.2. So, total we are getting 123 as an underflow. What will be the overflow? So, overflow will be the total extract, that is 40.5, in that solvent is this 24.3, okay, and oil is 16.2. So, total we are getting 163.5. So, this plus this, so we are getting 163.5. So, this total remains same in stage 1. Okay. So, analysis of stage 1 is that the oil concentration in the underflow, that is the product concentration, that comes 0.4, 40% was there, and it is an equilibrium stage. So, oil concentration in the underflow equals the oil concentration in the overflow, because all stage will be in the equilibrium. So, let x 2 represent the concentration of oil in the overflow from stage 2. Stage 1 we have calculated, and we have got that as equilibrium concentration in the product and the underflow is 0.4. So, stage 2 x 2 represent the concentration of oil in the overflow from stage 2 passing into the stage 1. Then oil entering stage 1 equals the oil leaving stage 2. Okay. So, okay, the oil entering here will be stage 2, from the stage 1 to it is coming to the stage 2. So, the oil entering at stage 1, oil entering at stage 1 equals the oil leaving at stage 2. So, since the solvent is coming from the back side, okay, so it is actually the oil which is leaving at stage 2, that is coming into stage 1, like that. Okay. So, therefore, the balance we can calculate. So, 63.5, that is the solvent which is having x 2 concentration, plus 18, that is the oil, that will be equal to 41 into 0.4 plus 40 into 40.5 into 0.4. So, this is the underflow and the overflow. Okay. And this is the initial stream. So, initial stream has x 2 if we assume, and that this 18 was in the feed stream. So, x 2 we are getting 0.23, okay, x 2 is 0.23. Now, since x 2 will be equal to y 2, because the concentration in the equilibrium will be same in the underflow and the overflow. Okay. So, x 2 will be equal to y 2. So, we are getting 0.23, because this will now enter in the this x 2 that remains in that stream, that will now enter into the next stage. So, similarly, in the stage 2, where we have taken that x 2 equal to x 3, and that is 0.23. So, this 41 into 0.4 plus this 63.5 into x 3 now. So, that will be equal to 63.5 into 0.23 plus 41 into 0.23. So, eventually, we are getting x 3 as 0.12. Okay. And this analysis will go on. We will take x 3 now equal to y 3, and that is equal to 0.12. Okay. So, if you just go back to the initial diagram. So, here we can see that that when in one stage, when in one stage the solvent is entering and the extract that is coming out, the overflow that is coming out, that is entering as a solvent in the next, okay, and the extract that is coming out, that is entering as a solvent in the next one. So, like that in the first stage, which is, if you consider the first stage. So, the exit of the second stage is entering, the overflow of the second stage is entering at the solvent in the first stage, right, and eventually the concentration will change in a way. So, x 1 that we are calculating. So, in the equilibrium stage, this will be same with the y 1. Okay. Similarly, the x 2 that stage will consider, that will similar to the y 2 and so on. So, will one after the other the stage will count, calculate. So, finally, in the stage 3, x 3 equal to y 3 0.12, and then we will do the balance. So, 41 into 0.23 plus 63.5 into x 4, that will be equal to 63.5 into 0.12 plus 41 into 0.12. So, we are getting x 4 as 0.049, like that. So, x 4, that means in the fourth stage we are getting this. And analysis of the stage 4, finally again x 4 equal to y 4 because of the equilibrium condition. So, 0.049, and therefore, the balance on the oil will be, again we will calculate in the same way, that is 41 into 0.12 plus 63.5 into x 5, that is equal to 63.5 into 0.049 plus 41 into 0.049. So, we are getting this much 0.00315. Now, the required terminal condition is that the underflow from the final nth stage will have less than 1.8 kg of the oil, because 90% extraction should be done. So, less than 1.8 kg. Now, that x n, if we try to calculate in the terms of fraction. So, x n is less than how much? X n, that the fraction we want to calculate, that is 1.8 out of 41. Okay. So, the stream has 41 kg of the solvent, in that 1.8 was there. So, at least lesser than this fraction we need to find out. So, 1.8 by 41 is 0.044, and here we are getting 0.00315. So, after fifth stage we are almost achieve the condition that 90% extraction of the oil has been done from the sample. Okay. So, this is how you can design when you want to set up any extraction, solvent extraction, or for example, you want to separate a leaching setup. For that you have to think about that what is your sample size and what is the flow rate and how much oil content the initial sample is having, and you want to separate what amount of or what fraction of the oil or solute you want to separate. So, based on that you can design that how many stages are required. Okay. And also in the yesterday's class we have discussed the efficiency calculation, that is by the Murphy efficiency, which based on what is the extraction can be achieved in the equilibrium condition, and if equilibrium is not achieved, so how far we can have that concentration, and the ratio of those two things we can use for finding the efficiency of each stage. Now, coming to the mass transfer in leaching operation. So, we have mentioned that it is a molecular transfer process. So, the equation of mass transfer we can write in this way, that dm by dt, that is equal to constant k dash into the interface area through which the transfer of the molecule is taking place into Cs minus C by B, where Cs is the concentration of the saturated solution in contact with the particles, okay, and C is the concentration of the solute in the bulk of the solution, at time t. Okay. So Cs minus C that will work as a driving force. A is the interface area and B is the effective thickness of the liquid film surrounding the particles, and mass of the solute, m is the mass of the solute, m is the mass of the solute transferred in time t, and k is the k dash is the diffusion coefficient. So, this is how having a diffusion means the molecular transfer process, considering it as a molecular transfer process, we can have this equation to find the rate of mass transfer. For a batch process in which V, the total volume of solution, is assumed to remain constant, then we can write this as the mass that will be transferred, that is equal to volume V, the volume V of the solution into dC. Okay. So, that is the concentration gradient. So, concentration generally we express in kg per meter cube like that, and there is meter cube. So, ultimately we can get the change in the mass. So, dC by dt that will be equal to k dash into A Cs minus C by B into V. Okay. So, this is concentration gradient. The time t taken for the concentration of the solution to rise from its initial value of C0 to a value C is found by integration on the assumption that both B and A remain constant. So, the thickness of the liquid film will remain constant, and the interface area, the contact area through which the transfer is taking place between the solid material and the liquid layer or liquid film. So, that will constant. So, from this we can write this equation, integration C0 to C dC by Cs minus C, that is equal to integration k dash A V into B dt. So, we are getting this equation as ln of Cs minus C0 by Cs minus C. So, in pure solvent the concentration C0 is initially taken as 0, there is no solute trace of the solute in that, and this is equal to k dash into A V B into T. So, further from this we can write as 1 minus C by Cs, that is equal to e to the power minus k dash into A by V B into T. Okay. So, again C will be equal to Cs into 1 minus e to the power minus k dash into A by V B into T. So, this is the equation of the change of concentration with respect to time in case of a leaching operation. So, let us see one example on that. In a pilot scale test using a vessel 1 meter cube in volume, a solute was leached from an inert solid and the water was 75% saturated in 100 seconds. If a full scale unit, that is 500 kg of the inert solid containing as before 28% by mass of the water soluble component is agitated with 100 meter cube of water, how long will it take for all the solute to dissolve? Assuming conditions are equivalent to those in the pilot scale vessel and water is saturated with the solute at a concentration of 2.5 kg per meter cube. Okay. So, first we have using a pilot scale vessel of 1 meter cube volume and the solute was leached from an inert solid and the water was 75% saturated in 100 seconds. Now, we will see that for the pilot scale vessel the concentration will be 2.5 into 75 by 100. Okay. So, we are getting 1.875 kg per meter cube, this is the concentration, and Cs in the saturated solution the concentration is 2.5 kg per meter cube. Volume of the pilot plant is 1 meter cube and time is 10 seconds, right. So, putting this in the equation, Okay, in this equation C equal to C s 1 minus e to the power minus k dash into A by B into V, because some parameter is given in this problem and some are not. So, those are not given, that terms will calculate from the pilot, because that ratio will remain same if we upscale this from the pilot to the actual scale. So, that ratio will make same, and then we will calculate what will happen in case of the actual system. So, we will put it here in the equation, value of C and C s. So, 1.875 equal to 2.5 into 1 minus e to the power minus k A by V b. So, V is 1 meter cube into B into time t. So, k A by B we are getting this. So, this ratio was required because this is not given in the question, and for the full scale vessel then concentration C will be 500 into 28 into 100 by 100. So, that the concentration is coming 1.40 kg per meter cube. C s is 2.5 kg per meter cube, V is 100 meter cube. So, if we try to get this, what will be the time required? So, that will be 9.9 minutes, just we put the value of k by b in this equation. Okay. So, we will stop here and we will continue in the next class. Thank you.